So last class we talked about starting the regression project. So right now we're going to talk about uh, how to actually do regression. So this first video is going to cover it using Desmos, and it's going to be a little bit more in depth. We'll talk about the vocabulary. And then the second video, I'll make one where we do a regression using Google Sheets. So definitely make sure you watch this one because this is going to have most of the content. Okay, so sorry again for using baseball data. It's really easy to download. But just pretend you care about baseball. Okay. So here we have a graph or a table of data where this column is the number of strikeouts that a team recorded in a game. And this is by the pitchers. So here the Angels pitchers were striking out 8.2 batters per game. And then here's the number of wins that the team had. And we're going to look at whether strikeouts and wins correlate strongly. So we're going to go to Desmos. And then we'll just click Start Graphing. So this is not like a teacher activity. This is just the blank Desmos calculator. And one of the great things about Desmos is that if you copy and paste a table of data, so I'm just going to highlight these two columns, and then, and then copy. And I'm going to go over to Desmos and paste. No, it doesn't want to let me paste like this. But if you press Control V or Command V on a Mac, then that will paste all of the data, and then it formats it into a table perfectly. And it graphs all of the points. So here's our data. So here I've zoomed in a little bit better. And we can see like some evidence of a positive relationship here. So it appears that as strikeouts go, as the team's pitcher's strikeouts goes up, the wins goes up. To do a regression in Desmos, what we do is we type in, so see here how it says Y1? So Y1 refers to the list of data. So if you type in Y1, Desmos automatically formats it as a subscript and knows that you're referring to that list. You could also, so without using the pop-up keyboard here, you could literally just type Y and then the number 1 on your keyboard. It does the same thing. So now to do regression, we don't want to do equals. This is not what we want. We're going to find, this one here, this little squiggly thing. It's also on a keyboard to the left of the 1 key, and you have to press Shift. So it'd be Shift, and I don't know what that button is, but we'll shift that, and you get the squiggly. Or you could press it from here. So Y1, squiggly, and then we know that like a linear function, you remember from Algebra 1, is y equals mx plus b. So that's what I'm going to type in, a linear function, but instead of typing x, I'm going to type in x1, just like I did for y1, and then plus b. And we have our regression output. So here's some important stuff. This is stuff that you definitely need to write down. So it gave me this little that little regression output window. So I'm going to go put this guy over here. Cool. All right. So what is this stuff, right? So our regression equation, so don't write this as your regression equation. The actual equation would be, I'm going to do insert equation and be fancy. Y squiggly, y equals, so here it gives me my slope. So it's 10.4154x. And then here's my y-intercept. So minus 5.87449. And it tells me r squared and r. So r is the measure, I want a lowercase r. R is, whatever. R is the measure of linear association. In a data set. So R will always be a number that is between -1 and +1, and it measures the strength and direction of a linear relationship. So what this tells it, so our, oh, and it's called the correlation coefficient. So we're actually going to use r squared more than we're going to use r in this class, because r squared is a better measure across all functions, and r can only be used for linear functions. So r squared r squared is called the coefficient of determination. And what r squared tells us is, mostly it's like r squared can be described as a kind of percent fit. So it tells us that in this function, so 57% of the variation between strikeouts per game, so that's strikeouts per 9 innings, and wins can be explained by this function. Some other cool things this tells us. So we know about slope and y-intercept. So the slope here is 10.41. So what we should remember about linear functions is for every time x goes up by 1, y goes up by 10.4154. So in the context of this situation, because the slope is 10.4154, we can deduce that for every 1 increase in strikeouts per game, the team is expected to win approximately 10 more games. And that's a very loose approximately, and it's important to write that because it's not like this function is obviously not perfect. An r squared of 0.57 is okay, but not great. So looking at our graph, we do have quite a bit of spread here, but it does appear, and there is enough evidence to suggest that teams who strike out more batters are in fact winning more games. Okay, so now we're going to get rid of this stuff, and we're going to look at another data set. So if we go back here to this sheet, now click on, so now we're going to look at home runs per 9 versus winning. So again, this is, oh wait, I changed it. We're looking at ground ball percentage versus wins. I'm going to rename this sheet ground balls versus wins. So this represents the percentage of times that pitchers got the other batter to hit a ground ball. So most baseball coaches would think that if the other team is hitting a lot of balls on the ground, that means they're probably not getting a lot of hits. And we're going to look at ground ball percentage versus the wins that the team had. So I'm going to do the same thing. Copy this data set, Control C, and then paste it over here. And what we see here is a pretty messy looking graph. So let's go ahead and do our linear regression again. And remember, you can just, if you type a y and then a 1 right after, then you'll get the y1 subscript. So this is exactly what you need to type in. And now let's look at our output here. So we got r squared of 0.08. So that is a really, really low r squared. So what that tells us is teams that get the other team to hit more ground balls, there's really no relationship between the pitcher's ground ball percentage and the number of games that the team wins. So if you find something like this in your project, this is a perfect example of something that a lot of people expect to have a strong relationship, but actually doesn't. So it's a really low r squared of 0.08. So this would also be a really cool thing to have in your project, where you expect something to correlate and then it actually doesn't. Okay, now we're going to look at one more example. So now we're going to go to this launch angle versus distance. So this is the launch angle of certain projectiles, and they were all launched at the same speed. And then this is the distance that the projectiles landed at. So we're going to do the same thing, copy and paste. And you can already see here, this is not forming a line, but we're going to do linear first anyway. So y1 squiggly mx1 plus b. Now, this gives us an r squared that's pretty good, 0.84. But before we jump ahead and assume that the linear model is fine, we're going to click on this plot of residuals. So what the residual plot does, if you turn your head about 45 degrees to the left, I wish I could turn the screen for you, then you'll notice that this looks exactly like this. It's just straight, it's just like made horizontal. So the residual plot is just measuring the distance from this point to this line. So this first point right here at 10, the line is at 148 and the point is at 115. So the distance between those two things is negative 32. And that's what the residual plot does. It just calculates the distance from this point up to this line. So same thing here. This one is only slightly below the orange line. So here it's only slightly below the x-axis. So what we use the residual plot here is we see this clear pattern here in the residuals. So we're going to write about residual plots. Measure the distance between the expected value from the regression equation and the actual value. And what they tell us, if we have a clear pattern in the residual plot, then a linear model is not appropriate for the data set. And we need to try something else. So this is the only case where you shouldn't use linear regression, is if you have what's clearly not, like this residual plot has a very clear pattern, as opposed to if we go back and plot the residuals for our strikeouts and wins. So I'm going to take these off for a second. So I go back and I plot these residuals, and we have to do y2 squiggly mx2 plus b. I'll zoom way in here. So if we plot these residuals, we have it's just scattered on both sides evenly. So here, because the residuals are scattered evenly above the x and the y-axis with no sort of like pattern like that, or like this, or sometimes you get a pattern where they go like this in both directions, so they get farther and farther away. But we don't have a pattern here. So in this one, the linear model is good. But it's our other data set where the linear model is not good. So let's put those back. My cat is very excited about residual plots at the moment. Okay, so because linear is not good, we're going to delete this. And we're going to try something else. So you guys remember quadratic functions. Quadratic functions usually look like x squared or ax squared plus bx plus c. So we're going to do a quadratic regression. We would type exactly that in, but y1 squiggly, and then change the x to an x1. Oh, both x's to an x1. There we go. And now we see a really, really good pattern. So we have r squared of 0.994. Our residuals, there's a little bit of pattern there, but not enough to, they're so close and the r squared is so good that it's safe to assume here that the quadratic model is probably the best fit. For fun, let's also do an exponential regression. So some of you might get data that comes out to be exponential. So let's run that one. So we do y1 squiggly, and exponential regressions are going to be a times a number to the power of. So to get the exponent, you press this button, this a to the b, and that makes an exponent. And then you can press x1. And here our exponential function isn't very good. Oh, we can add a plus a constant. That makes it quite a bit better. But the quadratic was still obviously the best fit. Okay, so at this point, I would encourage you to, you'll still want to watch the Google Sheets video. And the reason for that one will go much faster. But Desmos has a limit to the number of points that you can copy and paste. So if you have a data set that has over 50 points, and a lot of you will if you're doing data from the World Data Bank, then you'll need to do your regressions in Google Sheets.